Dear students, welcome to the lecture series on the topic Engineering Graphics. So today we will be continuing with the basics of the development of surfaces of solids. I am Dr. IPS Ahuja, Professor, Department of Mechanical Engineering, Punjabi University, Patiala. In the earlier lecture, we had discussed about the principles of the development of the surfaces, and we had worked out different types of development techniques over there. So the first technique we had discussed was about parallel line development method. So now in today's lecture we are going to discuss about few basic examples of parallel line development method and the radial line development method. So here we have a cube available with us. So this figure shows the front view of the cube, which is having the edge 50 millimeter. Now we are required to develop all the six faces of the cube, right? So usually whenever we are asked that develop the lateral surface of the cube, so then only four surfaces which are the lateral surfaces are there. Those surfaces will be developed. So the top and the bottom surface of the cube will not be developed in that case. Whereas since we have been asked to develop all the six faces of the cube over there. So just as we had discussed, so these are the two end faces of the cube. This is the bottom or the base of the cube. This is the top face of the cube. So from the two ends, we are going to draw these string lines over there. You see, these are the stretch lines. So we have drawn the stretch lines starting from the two ends of the solid. And then we know the edge is equal to how much? This is equal to 50 millimeter. So now we are going to draw this distance will be 50 millimeter, and then all the lateral surfaces. We know that there are four surfaces which are the lateral surfaces. So corresponding to the four lateral surfaces, edge of each of the lateral surface of the cube will be 50 millimeter. So the four lateral surfaces dimensioning we have done over here. Now we are going to mark these lateral surfaces between these stretch lines over there. So this is the dimensioning portion. Now this is the first cube. You see the height is equal to 50 millimeter and the width of this particular square will be 50 millimeter. Similarly, this is the next face number second of the lateral surface. It will be appearing adjacent to the previous surface over there, right? Similarly, the third one and the fourth one. So here we can see the total length of the lateral surface will be 200 millimeter, whereas the height of this particular surface will be 50 millimeter, and wherever there is bend or there is going to be joint over there, wherever this is going to bend, so these bends they will be shown with the help of the solid lines over there. So these are four, you can see squares over there, and if we fold the surface with respect to these, you see bend points which we have shown over here, we are going to get the lateral surface of this cube. But here we are required to develop all the faces of the cube. So we are going to show the bottom face as well as the top face of this cube. So just see, the face number 5 of this cube happens to be top face, and similarly the face number 6 for this cube will be the bottom face of this particular cube. So this way the 6 squares, that is 4 in a sequence series and one above and one below, so they will show the development of all the faces of the cube, right? So this way we will be able to develop the cube using the parallel line development method. So again I repeat, these are the stretch lines that we have, and all the lateral edges of the solid, they will be represented between these two stretch lines over there. So this is the top face and this one is the bottom face of the cube. So this is the description about the development of all the faces of the cube. Now the next one, again another case we are going to pick up regarding parallel line development method. So here we are going to carry out the development of a hexagonal prism. Side of the base is 20 millimeter, axis height is equal to 50 millimeter, and this hexagonal prism is resting with its base on HP or the horizontal plane such that one of its rectangular faces happen to be parallel to the vertical plane. So we are required to develop the lateral surface of the prism over there. So to begin with, we are going to show the top view. The top view of this hexagonal prism will be drawn on the horizontal plane over there, and this will be drawn below the XY reference line. And since this hexagonal prism is resting with its base on the horizontal plane, so the top view will provide us with the true shape of this hexagonal top or the base surface over there. And having drawn the hexagon, and why we have drawn hexagon in this orientation? Because we are provided with the information that one of the rectangular faces of this hexagonal prism happens to be parallel to the vertical plane. You see this face 5, 6, F and E. So this is the face which happens to be parallel to the vertical plane. So that is why we have drawn this hexagon in this orientation. Now having drawn this hexagon, next thing is the dimension is 20 over here, 20 millimeter. We'll work out the access point, and then since it is a prism, we are not going to join it dark over there. So these are all the construction lines. They are required to identify the access point of this particular hexagonal prism. So this will be obtained once you join all the three diagonals of this particular hexagon surface which we have drawn below the XY reference line. So having worked out the axis O and O1, O will be the top point of the axis, and whereas O1 will be the bottom point of the axis as usual. So now we know the axis height. So the height of the axis is equal to 50 millimeter. So we draw the 50 millimeter axis height. The moment we draw the axis height, you see, we know the construction of the prism over there. So now we can complete the front view, and since you can see edges A1, B2, C3 and D4, they are visible to the observer, as the observer is going to look at this prism from this side. So all the vertical edges, longer edges of this prism, they will be drawn dark. But another thing we need to remember in this particular case, that is the edge F6 and E5, they are lying farthest away from the observer and they are closest to the XY reference line. So F6 vertical edge and E5, they had to be drawn dotted over there. I am telling you, they had to be drawn. But since F6 dotted line projections over here, they have been overlapped by the solid line projection, that is the object line projections corresponding to B2. So the projections of B2, B dash, 2 dash, they are going to superpower or superimpose the dotted line projections of the vertical edge F dash and 6 dash. So again I repeat, the front view projections of corresponding to F6, that is F dash, 6 dash should be dotted, but they have been overlapped by the object line or the solid line projections corresponding to this vertical edge B2, that is B2 dash, B dash, 2 dash projections will be dark and F dash, 6 dash projections will be hidden. And since B dash, 2 dash projection, they are going to coincide with the dotted line projections of F dash and 6 dash, so we get a dark line over here. Similarly, the projections corresponding to edge E5, that is 5 dash, E dash, so they will be dotted, but these dotted line projections have been overshadowed by the solid line projections of corresponding to the vertical edge C3, that is the projection, that is the dark projections or the object line projections of the edge 3 dash, C dash, they are going to cover the dotted line projections corresponding to the edge F5 dash and E dash over there. So here we get the front view. Here we have obtained the top view of this hexagonal pyramid over there. Sorry, prism over here. Now let us draw the development of the lateral surface of the prism using parallel line development method. So you see, for this prism, this is the top end, this is the bottom end, or this is the bottom face and this is the top face. So two stretch lines we have drawn through the top face and the bottom face. So one thing we need to remember, while we are drawing the development, we need to have all the true lengths for all the edges. So please see, for the height, the true length is equal to 50 millimeter. So we have drawn 50 millimeter corresponding to this height. So the distance between stretch line will be the height of this particular prism, which will be true length and which is equal to 50 millimeter. How much is the edge of the base? Edge of the base is equal to 20 millimeter. So between these stretch lines, all the lateral surfaces, they will be marked over here. So let us see, I have marked this rectangle such a way that this height is equal to how much? 50 millimeter, which is true length. And how much is this length? Length, you see, there are 6 edges, A, B, C, D, E, F, and again back to A. So 20 plus 20 plus 20 plus 20 plus 20 plus 20. So 6 times 20 means 120 over there. So this length has to be 120. So this outer box length has to be 120. So this length will be 120, so that all these 6 edges, they can be accommodated over here. Now we can do the marking. Just see, for every edge I have done the marking that is equal to 20 millimeter. So all the edges, they will be equal to 20 millimeter. And then you see, I have marked A. I am starting the development from any one point. So I am starting my development from point A. So this will be capital A. I am moving in this, you see, anti-clockwise direction over here. So as I am moving in the anti-clockwise direction, so the second point encountered will be point B. Third point encountered will be point C. Fourth point encountered will be point D. Fifth point encountered will be point E, and sixth will be point F. But I have to get back to point A so that my surface should be completed over there. If I start from A and end my development at F, so I am going to miss out on one of the edges over there. So this thing must be remembered. So please see, I start from A, B is 20 millimeter, edge AB, edge BC is 20, edge CD is 20, edge D is 20, edge EF is 20, and again I get back to A. So the starting point is A, B, C, D, E, F, and again A. So that wherever I am starting from, I should be ending at the same portion. And having drawn these lines, now I need to join the lateral edges, that are the vertical longer edges I need to join. So this completes the construction of the development of the hexagonal prism using the parallel line development method. So here we have not gone for any cuttings, but it is just to demonstrate how the basics of the different solids, they can be obtained. Couple of cases of cutting we will also pick up, but those problems we are going to pick up from the next lecture onwards. Now the next one is, you have a cylinder. So cylinder of diameter 50 and height 60 millimeter, it is cut by an auxiliary inclined plane which happens to be inclined at an angle of 45 degree to the horizontal plane, and it is passing through the left top corner of the cylinder. So we are required to draw the development of the truncated cylinder. So you see, the top, that is the circle we are going to draw. So circle, we have divided it into 12 equal parts. So the diameter of the cylinder is equal to 50 millimeter. So since this is standing upright on the horizontal plane, so the top view will give us the true shape of the circular base or the top face. So 12 points we have marked, 1 to 12 over here. Now let us draw the front view. So the height of the cylinder is given to us as 60 millimeter. So height is 60 millimeter. Now all these projectors we are going to draw. So please check. This is our cutting plane. These are all the projectors through all the points, right? So 12 points are there. So outermost there will be 1 point each, and the inner, you see, projections, we have 2 points each on the inner 5 projection. So one projection point over here, see, starting with one projection at the last, and then interior 5, you see, projections which are there. We are having 2 points on every projection. Now you see, I have made the parity in the numbering. If this was 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Similarly, I have got 1, 1, 2, 1, 3, 1, 4, 1 and up to 12, 1 at the top surface over there. Now you see, this is the development of the top surface. This is the development of the bottom surface. But I need to remember one thing very carefully over here. That is, this particular cutting plane is going to pass through this corner, which should be there at this particular top corner over there, left top corner, and the angle of inclination is 45 degree with respect to the horizontal plane. So wherever this cutting plane is going to cut this particular cylinder, I am going to put down the names of the points of intersection. And since this cutting plane is going to pass through all the generator, you see 12 generators are there because I have divided this circle into 12 equal parts. So I am going to get 12 cutting points or 12 POIs onto every generator. So the starting point, I have again made parity, that is the serial number of numeral and the serial number of alphabets I have made. So A1 dash and 11 dash has been cut by cutting plane at point A dash. Similarly, 2 dash 21 dash has been cut by cutting plane at a point whose name is B dash. Similarly, the vertical projector, that is 3 dash and 31 dash has been cut at C dash. 4 dash and 41 dash has been cut at a point D dash. 5 dash locus line has been cut by E dash. 6 dash locus line has been cut by F dash. 7-1 locus line has been cut by G dash. Similarly, 8th numeral and 8th alphabet. So 8-1 dash and 8 dash vertical projector line has been cut by H dash. Similarly, 9 dash vertical line has been cut by I dash. 10 dash vertical line has been cut by J dash, and then 11 dash has been cut by K dash, and finally 12-1 dash and 12 dash has been cut by L dash, right? So 12 points of intersection we have worked out over here. But you see all these cutting points, POIs, they are lying on the vertical projector line. That is, every point of POI is lying on this vertical line. So that is why if we are going to look at these projectors from the top, points of intersections from the top, so these projectors, they will be available right here on the same line, right? So on the locus of 1, A will lie. On the vertical locus of 2, B will lie. On the vertical locus of 3 and 3-1, C will lie. On the vertical locus of 4 and 4-1, D will lie. Similarly, E, F, G, H, I, J, K, L, they will be lying on the corresponding locus line of the numeral value over here. Now, one thing more we need to remember, because you see this length ideally this should be equal to 2 pi r, or it should be equal to pi d. This length, it should be equal to pi d, but there is a limitation, because if I have to draw this equal to 2 pi r or pi d, then I needed to have some instrument available with me through which I could have measured this arc length over there. You see, this is all arc. 1, 2 is an arc, 2, 3 is an arc, 3, 4 is an arc, and 4, 5 is an arc. I don't have any instrument through which I can measure these arc lengths over there. So the instruments I am having the divider, I am having the scale, I am having the compass available with me. So my compass, scale or divider, they will be measuring the linear distance between this point and 1 and 2. They will not be measuring this arc distance. Okay, so this is an approximation method that whenever in the manual drawing we are going to mark all these 12 points, ideally the distance between point 1 and point 2, and similarly between all the subsequent points, they should be equal to 2 pi r divided by 12, so that the 12 sectors they are available. But in engineering drawing we are not allowed to use the mathematics over there. So we are going to use the method of construction to draw different points over here. So you see, if I have to measure this arc length, I don't have any instrument. Ideally I should have measured the arc length. So what I am measuring with my limitation, using my scale, I am measuring the chord length, that is a straight line distance between point 1 and point 2. So this will be shorter than this arc length distance over there. So my divisions which I have marked over here, they will be slightly shorter than the actual 2 pi r measurement length over there. So we call that whenever we are working on any specific problem regarding cone or any specific problem regarding cylinder, so we are using an approximate method because of the limitation that we have with our hand, that we don't have any instrument with us which is going to measure the arc length. So rather than measuring the arc, we are going to measure the straight line distance, that is the chord length between these 2 points. So these gaps which we have shown over here, they are marginally smaller than the actual lengths which should have been there. So the cylinder which we are going to obtain, or the length which we are going to obtain using the manual drafting, will be slightly shorter one. It will be on the slightly shorter side. But if you want to have the perfect development, what you can do, you can work out mathematically 2 pi r and then divide it by 12, and then this will give you your sectors over there. All these sectors will be pi d divided by 12. Okay, but we are going to follow the principles of the manual drafting. So in the manual drafting, this distance is the chord length, that is the straight line distance between point 1 and point 2. It is not the arc length distance between point 1 and point 2. So please see, I have marked all these points. I have started developing this. I have cut it over here. I have cut this solid over here, and I am going to open it like this: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and again I have to get back to 1, so that this joint is available at the point number 1 over here. So just see, I have marked the chord lengths over there. Again I am repeating time and again, not the arc length. So the total length will not be equal to 2 pi r or pi d. It will be slightly shorter than that, but otherwise the procedure will remain the same. Now you see, I know that point A lies on, you see, vertical length of 1 and 1, 1. Point B lies on vertical length of 2 and 2, 1. Point C will lie here, D will lie here, E will lie here, F will lie here, G will lie here, H will lie here. Then similarly you move on to, you are going to get point L, right? So A, B, C, D, E, F, G, H, I, J, K, L. So this way again I will get back to point A over here. Okay, so this way I have to locate the location of all the POIs which were located in the front view onto my development over here. So the simple development of the cylinder without cutting would have been only this one. That is why I have not started making the development for the cut section. I have restricted till now to myself to the development of a cylinder which has been divided into 12 equal segments over there. So the construction limitation I have explained, that rather than drawing or marking over here the arc length between 1 and 2, I am able to mark the chord length between 1 and 2 because my instruments don't allow me to measure the arc length. Now having drawn the development of the cylinder without the intersections, now I am going to work out how this particular development would look like if this cylinder has been cut by this cutting plane. So you see, these are the points of intersection. Once again, 7, you see, pairs they have been identified. The first point and the 7th point, they will have only 1 point, whereas the interior 5 points, this projector, this projector, this projector, this one and this one, they will all have 2 points upon them. So now you see the total length, ideally, this is what I was trying to explain. Total length, you see, this should have been equal to pi d, which it is not in the manual construction. You see, I am supposed to measure this arc length, but my instruments don't allow me to measure this arc length. So what I am able to measure? I am able to measure this chord length, which is the shortest distance between 2 points. So my divider will measure this, my compass will measure this, and my scale will measure this. So limitation is I am not drawing the chord length distance over there, arc length distance over here. Rather, I am going to show only chord length. So this chord length will be shorter than the arc length, even though marginally. So in every, you see, chord length, I am going to reduce my length by around 1 to 1.5 millimeter. So total length will be reduced by approximately by 13 to 15 millimeter in the 12 sectors over there, right? So that is the limitation of the manual method. So here we are going to start with the now location of these points of intersections in the development view. So please see my point number A dash, please check, my point number A dash was lying on the vertical projector 1 dash and 1 1 dash. So if I draw a horizontal line through this, it is going to intersect 1 1 dash over here, 1 and 1 1 over here. It is also going to intersect 1 and 1 1 over here. Just see, we have marked one point over here, we have marked another point over here. So the names of both of these points, they will be small a. So this is the point which is there at which my cutting plane is going to intersect with my cylinder over there. Now the second points, you see, second points are B dash and L dash. Please check the second point of intersection. Now there is a pair, B dash and L dash comes in a pair, where B will be located on the vertical edge of point 2, whereas L will be located on the vertical edge of 12 and 12 1. So B will be located on the vertical edge of 2 and 2 1. So now I know the location of B and B dash and L dash. Now I'll move this point horizontally till the edge 2 and 2 1 is encountered and the edge 12 and 12 1 is encountered. So both of these points, you see, I have plotted 12 and 12 1. You see, it is going to take care of POIL. Similarly, my vertical edge 2 and 2 1, it is going to take care of my cutting point B dash, that is B over here. So the second POI has been located corresponding to this projector. Now this projector is also going to have two POIs. Which are those POIs? They are C and K. Please check. This horizontal, you see, projector is going to have my two POIs, which is C dash and K dash. Where does C lie? You see, C lies on the line 3. So line 3 means vertical edge of 3 and 3 1. C lies on the vertical edge of 3 and 3 1. Whereas K lies on vertical edge of 11 and 11 1. So let me see onto this horizontal line. Where does 3 lie? Here my C point will be located, right? And where does 11 and 11 1 lies? Here. So here my point K will be located. So just see C and K, both of them, they have been located over here. Next, this is my fourth vertical projector. So it houses, it locates my two POIs, which happen to be D dash and J dash. Now I draw the horizontal projector. Where does, you see, D dash lie? D dash lies on, or D point lies on vertical projector 4 and 4 1. Where does J lie? J lies on the vertical projector 10 and 10 1. So from this locus line, let us see where 4 and 4 1 lies. This one. Where does 10 and 10 1 lie? It here. So here my point D will lie. Here my next point J is going to lie. Similarly, this is again one vertical projector H, which is going, or generator, which is going to take care of my two of my POIs. Which are those? These are E dash, right, and I dash. Now where does E lie? E lies on the vertical projector, you see, 5 and 5 1, and I lies on the vertical projector 9 and 9 1. So through this, now I draw the horizontal projector, find out where 5 and 5 1 lies. Here my E point will be lying, and next I work out where does my 9 and 9 1 lies. So here my I point will be lying. So again in pairs I am going to work out my POIs in the development view. Next, here my sixth projector is there, vertical edge projector or the generator, onto which my cutting plane is cutting this generator at F dash and H dash. So let me look at this in the top view. F will lie on the vertical generator of 6 and 6 1, and H will lie on the vertical generator of 8 and 8 1. So from this locus I draw the horizontal line and work out where 6 and 6 1 lies and where 8 and 8 1 lies. So where 6 lies I locate F, and where 8 and 8 1 lies I locate H over here. And finally this is my G point. It lies on the vertical projector at 7 and 7 1. So through G dash I draw the horizontal line. Wherever it intersects 7 and 7 1, I get the location of G. So you see 12 POIs were there. because my cutting plane was passing through all the generators. So all 12 POIs, they have been located in the development view. Now this portion has been cut, so this is discarded. So now the vertical edges will be drawn straight, and this edge, all these 12 points, they will be joined with the help of a freehand curve. So this completes the development of a cylinder which has been cut by a cutting plane passing through the left corner of this cylinder over there, right? Next, so it is just like if you roll this cylinder, this is what we have been proclaiming. You roll this cylinder by 360 degree, so you are going to get this length as pi d. So in rolling you will get this length as perfect, but not while constructing. So while you are constructing, so rather than drawing the arc length, we are able to measure only chord length. So whatever we are able to measure, this will be slightly shorter than the actual pi d. If you want to draw the true over here, then draw each sector is equal to pi d divided by 12 over there. So that is why, since this length is shorter while we are doing the manual construction, we call this method as development. So whereas there is compromise only in the length, in the height we are measuring the true length only. So height is true length. This is slightly shorter than true length because of the manual limitations regarding the construction over there, right? Then the next is the development of the pentagonal pyramid. So here we have a pentagonal pyramid, and we are required to draw the lateral development of the pentagonal pyramid having base edge 30, and it is having one edge perpendicular to VP. Just see, it is going to have one edge perpendicular to VP. So we have drawn it in this orientation, right? So this is one edge which happens to be perpendicular to the vertical plane. So edge is given to us 30 millimeter. We'll work out the axis. Axis we'll be working out, draw perpendicular from every corner, and it should be meeting the bisector of the opposite edge. So from every corner, draw bisector of the opposite edge. So 5 locus lines, they have been found out, and intersection of all these 5 locus lines, they will provide us with the axis point. And then since it is a pyramid, all the slant edges, they are visible from the top. So we are going to join all the slant edges of the pentagonal pyramid over there. So axis has been located. Now we'll draw the axis height. Axis height is given to us as 60 millimeter. So we work out the 60 millimeter height. So these are the base points corresponding to the base. So the front view projections will be these on the XY reference line on the HP. And now having located the axis height, so O dash point has been located, and then the slant generators we are going to join. Okay, so once again, the front view of OA, that is O dash A dash, should have been hidden because it is lying on the back side, but these projections have been once again covered by the solid line projections of OB. Similarly, the projections corresponding to OE, that is O dash E dash, should have been dotted, but they have been again superimposed by the object line or the dark projections corresponding to OC over here. So that is why both of these projections, they have been drawn dark. Next, so here you see, is this slant edge true length? No. Why this is not a true length? Because OA and OB happen to be inclined to the vertical plane. So O dash A dash and O dash B dash will not be true length. Similarly, OE and OC, is this slant edge true length? No. Why? Because OE and OC, they don't happen to be parallel to XY reference line or the vertical plane. Therefore, O dash C dash and O dash E dash, they will not be true lengths. But there is one edge of the slant edge. Just see, this is my slant edge OD. This happens to be parallel to the XY reference line. My slant edge OD happens to be parallel to the XY reference line. Therefore, O dash D dash, which is available to me, that is the length of the slant edge, it should be true length over there. So this is using the basic fundamentals of rotation of line, basic principles of projections of line. Whenever a line or the apparent length happens to be parallel to the XY plane, so on the opposite side, that is on the front view, we are going to get the true length. So O dash D dash is the true length of the slant edge, and we have discussed in the previous lecture, in order to draw the development for the pentagonal pyramid using radial line method, two things they are required. One is true length of the slant edge and the edge of the base. So edge of the base true length is already available with us. This is 30 mm. So I needed to work out true length of the slant edge, but there are 5 slant edges available. So I am evaluating each one of them one by one, right? So that I evaluate which one is the true length over there. Now you see, I know the edge length. Once I know the edge length, I am going to have my radius as the edge length of the slant edge, which is equal to O dash D dash. Just check. O dash D dash is the true length of my slant edge. I have drawn this radius, and having drawn the radius, now you draw an arc over there. Once you draw an arc, then you mark this distance. How much? 30 millimeter. This is the edge length. So first arc, one edge, second arc, second edge, third arc, third edge, fourth arc, fourth edge, fifth arc you draw. So 5 edges we will be able to locate. And now having located 5 edges, you see starting point is O. This is my radius, which is equal to the slant edge, which is true length, O dash D dash. And now 30 millimeter. Now this is not the arc length, this is the chord length basically. So I am going to mark all these chords. So this is 30, this is 30, this is 30, this is 30, this is 30. You start from A, B, C, D, E, and then A. Just see, I start from cutting from A. I start from A, B, C, D, E, and then A. So that I am ending up at the same point. So this is the development of my pentagonal pyramid using the radial line development method. So here I have a center, and then this arc is only there for the construction. This is not the part of the development. So the straight edges will be the part of my development because the base is straight. So had it been a cone, so I would have used the outer cover over there. Outer circle or arc I would have used over there. Then here is the frustum of the square pyramid. So in case of a pyramid, you see this is the true length of the slant edge, and this is the edge of the base. So this is true length of the edge of the base. This is the true length of the slant edge. And now you see, we are going to take this as the radius. What is frustum? Frustum means this has been cut at the center over there. Okay, this has been cut with respect to the base. Cutting plane will be parallel to the base. That is the measurement of the frustum, meaning of the frustum. So you see, this is the original frustum without cutting. So this is my original slant length. This is my truncated slant length, true length of the slant which has been cut over there. This portion has been cut, but this is the true length of the cut portion. So now you see, I am going to draw arc regarding the full length, and then I'll be drawing this radius over here, and then how much is the edge, whatever is the edge length, true length over here. I'll be making 4 cuts. So 4 edges I have to show. Edge 1, edge 2, edge 3, edge 4. So 4 edges I have drawn. Now I am going to join each one of them so that the isosceles triangles, they can be joined. Right? Now this is my cut portion. This is my cut portion. So corresponding to this, once again, this is my slant edge for the cut portion. So I am going to draw another arc over here. Just see, I am going to draw another arc corresponding to this shortened length, whatever cut portion is there. And this is the true length of the, you see, this is the true length of the cut portion over there. So this was bigger, this is smaller. So this smaller edge also, 4 edges I will be drawing over here. So first smaller edge of the cut portion, second smaller edge of the cut portion, third smaller edge, and the fourth smaller edge. And then I will be joining the remaining slant edges. So these are the slant edges which are visible to me. So this completes my development of the square pyramid which has been cut by a cutting plane parallel to its base. So we call it frustum of a square pyramid. Similarly, we have this cone we have already discussed, that is the theta angle or the included angle should be R by L multiply by 360 degree. So here we have been provided with diameter is equal to 50 and slant length H is equal to 75. So once we know the slant length H 75, so we'll take this as the radius, draw this, and then I know the angle, included angle. So I'll draw included angle as 120 degrees. So I don't need to measure. You see, I don't need to measure the arc length over there. So 2 pi d I don't measure. So without measuring 2 pi d, just by using this equation, I have been able to develop this cone using this formula over there, right? So practically this will be nothing but this will be equal to 2 pi r or pi d. Okay. So here we go. Last one, that is radial line development for a cone over there. Here we have a cone and we are required to draw the development of the curved surface of this cone over there. Now we are given that the diameter of the cone happens to be 50 millimeter and the axis height of the cone happens to be 65 millimeter. So let us start working on the projections of the cone first of all. Then we will be starting with the development of the curved surface of the cone. So the top face, you see, it will be the circle, that is the, if you are going to look at the cone from the top, so the top view will be a circle and we have divided the circle into 12 equal parts so that we get better view of the development over there. So these are the 12 parts, that is each sector will be equal to 30 degree in this particular case. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So these are the 12 parts, and then from 12 to 1 again we will be coming back. Now we draw the front view. In order to draw the front view, we should know the axis height, which is equal to 65 millimeter. So we have drawn the axis and marked 65 millimeter over here. So O dash will be the top apex point or the vertex point, whereas O1 dash will be the base point, and these are the projectors of the base which are obtained on the horizontal plane. Now one thing we need to understand very carefully in this case, that is, in case of a cone or in case of any of the pyramids, two things we will be requiring. One is true length of the slant edge. You see here we have 12 slant edges over there, 12 slant generators are there. So we have 12 slant generators and all of them, they are not giving you the true length. So which are the slant generators which are going to provide us with the true length? We must refer to this figure, and the principles of rotation of line or projections of line, we need to have proper understanding about it. So please check the top view of the projector O1 and similarly the top view of the projector O7. They both of them, they happen to be parallel to the XY reference line, and since the apparent length of the top view of the projector O1 and O7, they are parallel to XY, therefore the front view of the projections of the slant generator O-1- and O-7-, both of them, they will be true lengths over there. So this thing must be understood, whereas you see O2, O3, O4, O5, O6, O8, O9, O10, O11 and O12, all these slant generators in the top view, they are not parallel to XY. So the front view corresponding to these generators, they are not true lengths over there. So you see whatever light lines we have drawn over here, all the interior 5 slant generators, they represent the apparent length of the front view generator over there. So in the case of a cone, there is a better flexibility that there will be two outermost generators corresponding to O-1- and O-7-, which are going to present us with the true length of the slant generator over here. And we need only two things in order to be able to draw the development. We need, number one, the slant generator true length which is available, that is you can choose O dash 1 dash, you can choose O dash 7 dash, and both of them they happen to be equal. So this is what the note we have also added. Since O7 or O1 they happen to be parallel to XY, therefore O dash 7 dash and O dash 1 dash will be the true length. So the radius of the arc which will be drawn, this will be equal to either O dash 1 dash or this will be equal to O dash 7 dash, which happens to be true length of the slant generator. So I know the radius. Now once I know the radius, now I have to draw the arc over there. And another thing I need to understand, because we know that the development of a cone, it will be basically a sector of an arc in which the theta, that is the included angle of that arc, should be 360 multiplied by r by L. But I have already told you that we are not allowed to use mathematics in the manual drafting. So what we are going to do, we are going to draw these development using manual drafting. So in order to draw manual drafting, now as I told you earlier just 10 minutes back in this lecture, that in the case of cone or in the case of cylinder, we have to assume another approximation that is, we are not able to measure this particular arc length between different sectors over there. You see, these are all sectors which are having 30-degree included angle. So ideally we should have measured this arc length 1 to 2, but we are having only scale or a compass or divider available with us. So because of the limitations of the manual drafting, we are able to measure this chord length, and this chord length will be slightly shorter than the arc length. So whatever development we will be able to obtain, this development will be slightly shorter than the actual one. But if we are going to work on this system for the industry, there we are using the computerized drafting. So their arc length can also be measured. So we'll be able to put arc length over there, and the appropriate size of the sector of the arc can be measured over there, and it can be observed and it can be drawn. It's not that we cannot draw it, but here since we are using manual drafting only, this is the limitation in manual drafting. For the industrial drafting, there is no problem to measure this arc length over there. There we can just say we'll measure pi d or 2 pi r and divide it by 12. So 12 equal segments will be available over there, and we will be able to develop 100% accurate development for either a cylinder or a cone. It is only in the manual drafting that we are not able to measure this arc length, right? So now this will become our approximate development method only for manual drafting, not for industrial drafting, not for the computer aided drafting over there. So let us start working on the development. So here you see, I know the radius of the slant edge. So with O dash as center and O1 dash as the pencil point, I will be drawing an arc over here starting from point O dash. So having marked this radius of the arc is equal to O dash 7 dash or O dash 1 dash. Now the next step is I have to do marking. This is my point 1, point 2, point 3, point 4, 5, 6, 7, 8, 9, 10, 11, 12 and 1. So I'll start from 1, go to 12 and then get back to 1. So all the 12 sectors of this particular circumference of the circle have to be plotted over here. So ideally I should have plotted the arc length, but as I have told you, I am going to put forward only the chord length because of the limitations of the manual drafting. So please see, now the 12 arcs I am going to draw. Starting from 1, this is my serial number 2, serial point number 3, that is second point, third point, fourth point, fifth point, sixth, 7th, 8th, 9th, 10th, 11th, 12th and get back to 1. So you see, I have started from 1, I am moving forward till 12 and then getting back to first point, so that my starting point and the end point, they should be same. This is my starting point, this is my end point. Now I am going to draw radial generators from this apex point onto every point of this arc, so that I should obtain the radial generators over there in the development. So this is the development of a cone. You see, this is the development of a cone. Only thing is, because it is the manual drafting, so this sector, that is the angle of the sector, will be slightly shorter, maybe 1 to 2 degree or 3 degree. It will be shorter than the actual or the desirable one. But if we are going for computerized drafting or the industrial drafting, so the accurate measurement of this length of the arc will be 2 pi r, or it will, the length of the arc will be equal to pi d, that is the circumference of the circle. And once you are able to get circumference of the circle, once you roll it out, the perfect cone you will be able to obtain over there, right? So it is not the limitation of the drawing, it is the method of drawing that we are using over here. We are getting a slightly shorter sector over there. Otherwise procedure remains the same. Only thing is, rather than using this, you just mark the arc lengths over there. You will be getting the perfect cylinder or this perfect cone to be manufactured over there. So this is the procedure for construction of development of the curved surface of a cone over there, right? So we knew the radius, we knew this slant edge, and from that we are able, because both of them, they were true lengths. As I told you, true length for everything is required. So only the construction method limitation has put some limitations over there. Otherwise procedure remains the same. So this is was slant edge. Now I can darken this sector which has been obtained. So if I roll this sector, whatever sector has been obtained, I will be getting the formulation of the cone over there, which will be a hollow cone, right? So using sheet metal, I'll be able to work out the development of a cone, and using the same principles as that of development of a cone. Now this is the development of frustum of a cone. So what is a frustum? Whenever a solid is cut by a cutting plane parallel to its base, the remainder solid which is obtained is called frustum of a solid or frustum of a cone. So you see, this was the original cone which was uncut. So this is my original length of the slant edge or the slant generator, right? I know the radius of this particular base. So the radius is known, the slant edge is known. So what I will be doing, I know the true value of this slant generator, actual value or the true length of the slant generator. So using this slant generator as the radius, which is the true length, I am going to draw an arc over there. And using this formula, theta is equal to r by l into 360. So I'll be able to draw this sector over there. And even if I am going to do it manually, I will not be using this formula. I'll be cutting 12 arcs over there, starting with 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 and 1. So all the arcs I'll be cutting, and just like in the last slide we have seen that how to draw the construction of a development of a cone. So same procedure can be followed. So either you can use the formula, or even in the manual drafting I can obtain the development of a cone. Now this portion of the cone has been cut, and what will be, you see, removed, this will be again a smaller cone. The portion of the cone which has been removed, it is again a smaller cone. And for the smaller cone, this is my true length of the slant generator for the smaller cone. So this is my true length of the slant generator of the cone portion which has been removed. So corresponding to this, again I can draw a smaller arc, and once I draw a smaller arc, and once again all the 12 points I'll be marking corresponding to the smaller circle. Now these 12 points, you see, I had marked corresponding to the bigger circle. There will be another circle which will be corresponding to the smaller circle. So I'll be drawing this smaller circle and dividing it into 12 equal parts. And once I divide this smaller circle into 12 equal parts, so the length of one sector I will be measuring, and same way this will be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 and 1. So all these points I am going to mark corresponding to the sectors of the smaller circle, and then I am going to join this dark because this portion has been removed, so I will be joining this portion dark. So this sector gives me the development of the frustum of the cone, and once I roll this out, I am going to get this hollow cone being formed with the help of rolling off and joining of the two ends of this particular sector over there. So this is the construction of frustum of a cone. So with this, we have completed the basic structure, that how to obtain the development corresponding to the parallel line development method, and how to obtain development corresponding to the radial line development method for the simple solids over there. So this was the complete introduction about the development of surfaces of the solids. So from the next lecture, we'll be starting with the problems in which the solids which have been sectioned, so how the development of those solids will be obtained using this particular method, that is the development of surfaces of solid. So thank you very much. Thanks a lot.